Good afternoon, everyone. So our speaker today is EunjeongYi from University of Texas A&M at Galveston, and she will be talking on the maker-breaker resolving game on graphs.
Thank you, Nadia, for inviting me, and thank you everyone for showing up to my talk. And then sorry about the technical issues that I encountered earlier. So I would need assistance throughout the talk from Nadia. And so next, please. So outline of the topics would be as follows. First part would be on what maker-breaker game is, and then I will have to mention resolving set and metric dimension to incorporate that concept into maker-breaker game. And the second part is the general sense of maker-breaker resolving game. And the third part would be, if the time permits, it's going to be on fractionalization of those things. Next. So background of maker-breaker game, it goes back to 1973. Eldwash and Selfridge introduced maker-breaker game played on a hypergraph, H of vertex set being V and E being a set of hyperedges. Two players named maker and breaker alternately select a vertex from V, not yet chosen in the course of the game. Maker wins the game if he is able to select all the vertices of one of the hyperedges from E. Otherwise, breaker wins. Next. Duchenne, Gladel, Pearl, Renault introduced maker-breaker game applied to a domination game. So maker-breaker domination game in 2020. And this game is played on a graph rather than hypergraph, and can be described as the maker-breaker game on the hypergraph with the same vertex set as graph G and with the hyperedges corresponding to the dominating sets of graph G. Next. And Kang et al. Introduced a couple of years ago, maker-breaker resolving game. So this time we are applying the concept of maker-breaker game onto a resolving game. So this game is played on a graph G by two players. We call them resolver, which corresponds to maker, and spoiler corresponding to breaker. So resolver or spoiler who alternately select a vertex of G not yet chosen, and resolver wins if at some point the vertices chosen by him form a resolving set of a graph G. Otherwise, spoiler wins if she can prevent resolver from occupying a resolving set of the graph G throughout the course of the game. Next. And the fractionalization version was introduced actually toward the same year later. Next. So for this talk, a graph G is finite, simple, undirected, and connected graph with a vertex set V and edge set E. Next. So for distinct vertices X and Y in V, that R of X, Y is a collection of all vertices Z such that Z distinguishes X and Y by its distances. So where we denote D of U, W as the minimum number of edges on a path connecting U and W in a graph G. So a set of vertices S is called a resolving set of a graph if S intersection R of XY is non-empty set for every pair of distinct X and Y in V. Next. So the metric dimension of graph G denoted by dim of G is the minimum cardinality over all resolving sets of graph G. So if you look at the, thank you. So if you look at the second bullet here in the same slide, S intersection R of X, Y is non-empty set. That corresponds to the saying that if you pick any two distinct vertices, there exists a vertex Z in S such that Z distinguishes X and Y by each distances. So for an ordered set S, U1 through UK, it's ordered set of distinct vertices. The metric code of vertex V with respect to S is the K vector, which we denote by code of S subscript W, is distance between W U1, distance between W U2, distance between W UK, etc. Next. So some of you guys might be familiar with this picture. So let's consider a house with only one-story building with the floor plan looking like the first picture. And you have 5 rooms. And we wanted to install sensors in certain rooms, so that if there's a fire breakout, we wanted to be able to locate exact room so that we can just control the fire. So the question is, how many sensors do we need? That's actually the concept of metric dimension. So let's say this floor plan can be represented by a graph where room is a vertex represents each room, and two vertices are adjacent if and only if two rooms share a wall. So this graph G is a representation of this floor plan. And now if you look at it, let's say you install first sensor in room A. With respect to room A, you can in fact see the distance with respect to room A is 0. Neighbors would be 1. The next one would be 2. So the first coordinate of these vectors indicate the distance with respect to room A or vertex A. Now, again, you can see that with the one sensor, it's not enough to be able to exactly locate where fire broke out. So we need another sensor. So let's say we selected a sensor, installed a sensor in room C. So with respect to room C, let's see what happens. The second coordinate of these vectors, distance is 0, and its neighbors would be 1, and the other one would be 2. Now, if you look at all these 5 vectors, they are all distinct. So we can say that the vertices consisting of vertex A and C, they actually resolve the entire graph. Next. So the set consisting of A and C, vertices A and C, is in fact a minimum resolving set of the graph. As I said earlier, with the one sensor installed, it's impossible to exactly locate where fire broke out. Another thing that is worthy of mentioning is that metric dimension of a graph is 1 if and only if the graph should be a path. So this is a well-known result. Therefore, in this case, metric dimension of this graph equals 2. Next. So what is the background of metric dimension? So there are two groups of people. Slater in 1975, as well as Harari and Melter in 1976, studied the same concept of metric dimension. Harari and Melter used the terminology metric dimension, whereas Slater used the location number, because we are locating sensors. So that's one way to look at. Next. So applications of metric dimension can be found in robot navigation, sonar, combinatorial optimization, etc. There are a bunch of those applications that people mention in other papers, and I cite them. Next. It's known that determining the metric dimension of a general graph is an NP-hard problem. Next. So we are done in terms of just giving you a background as to what metric dimension is. Now what we are interested in here is that what would form a resolving set? So it doesn't have to be a minimum resolving set, as you can see throughout this talk, but we are mainly interested in about forming resolving set throughout the course of the game. So what is the motivation for MBRG? So suppose a company X tries to secure its network by installing transmitters at certain locations within the company, so that the robot is aware of its security status at all times, and thus identifying the exact location or a specific computer with a virus infection in the network. Whereas a rival company, Y, tries to prevent X from forming a secure network by occupying or controlling strategic locations or computers within the network of X. So with this application in mind, considering the time constraint, i.e., the longer it takes for a player to win a game, the more it costs for the player. So Maker Breaker Resolving Game was introduced by Kang, Klavza, Yiro, and myself in 2020. Next. So what is the rules? What are the rules of MBRG and the terminology and notation? So Maker Breaker Resolving Game, so we abbreviated as MBRG, is played on a graph G by 2 players, resolver and spoiler, denoted by R star and S star respectively. And they alternately select, without missing their turn, this is the important part, a vertex of a graph G that was not yet chosen in the course of the game. So if a resolver plays first, then we call it R game. If a spoiler plays first, we call it S game. So resolver wins the MBRG if the vertices selected by him after finitely many turns form a resolving set of a graph G. Otherwise, resolver fails to, otherwise the spoiler wins. So the outcome of, so what we assume is that each player plays optimally. Resolver wants to occupy vertices that form a resolving set, whereas the spoiler would do her best to prevent resolver from forming a resolving set, occupying resolving set. So the outcome of MBRG of a graph is denoted by, we use the small o of G. And so the outcome, there are, actually one can view it as 4 possibilities, but in fact there are 3 realizable outcomes. First, resolver wins regardless who played first. So that's R, curly R. S, outcome being S being spoiler wins regardless of who plays first. Whereas N stands for neutral, right? So the first place win, the first player wins. So in that case, we call N. Now, the question as to whether the second player would have an advantage and win. So that doesn't happen. So there was a mentioning of that could go back to the earlier work of Maker Breaker game. Next. Any questions so far, by the way? So please feel free to interrupt me and ask me questions if you have any. Okay, so first I mentioned to you about the outcome of Maker Breaker resolving game denoted by O of graph G. Now the second one is the minimum number of steps that a player to win, right? So the Maker Breaker resolving number we denoted by R subscript MB of G is the minimum number of moves of a resolver to win the R game, provided he has a winning strategy. So if you look at the third bullet, the Maker Breaker spoiling number, which we denote by S of MB of G, is the minimum number of moves of the spoiler to win the result, the game R game, provided that she has a winning strategy. So if you look at R of G versus S of G, those are the situations when resolver played first. Whereas if you look at the second and fourth bullets, when there is a prime, that means that spoiler played first. So that's the difference. Next. So let's look at 3 examples. So if you look at a path, the first one, when you pick an end vertex, you can see that it's going to resolve the entire vertex at 0, 1, 2, 3. So therefore, whoever can occupy an end vertex, that person wins. Whether resolver plays first or second, guaranteed to pick one of these 2 end vertices. Therefore, the outcome is that resolver always wins. Now let's look at the second graph, G2. Now, if you look at G2, there are 4 leaves, right? 4 leaves. So among these 4 leaves, if you pick any 2, you can see that except themselves, nobody can distinguish them from by distances. So any 2 leaves, we are going to introduce the concept of twin equivalence class very soon. But these 2 leaves, they have identically same neighbors. So when you pick these 2, at least one of them must belong to any minimum resolving set. In other words, out of these 4 leaves, 3 of them must belong to any minimum resolving set. So as you can see, after the second round, spoiler is guaranteed to pick 2 vertices out of 4, which means that resolver can never occupy 3 vertices. So spoiler is guaranteed to win. So the outcome is S. Now, finally, the third one. So we have, I wish I had a mouse moving around, but thank you, Nadia, for doing this job. So you have 3, sorry about that. You have 3 leaves together with the 2, the last one. So these 2, you can just pick one of these 2 vertices. And out of these 3 leaves, you just need to occupy only 2. Then you are guaranteed to win. It forms a resolving set. So if you are spoiler, the spoiler could occupy 2 of the leaves after the second round. So spoiler would win. Now, if you are a resolver, you can occupy the first end vertex, and out of these 2 leaves and the other 2 vertices, along the path of connecting to the major vertex of degree at least 3, you can pick one of them. So resolver is guaranteed to win. So with respect to the question of, well, how do we know whether, if you are given a tree, how do you know whether what kind of set of vertices would form a resolving set? That actually goes back to the result by Hwasong and Zhang. They actually characterized it, and we actually rely on that. So thank you. Next. By the way, is this clear to you guys, the previous one, in terms of examples?
Yes.
So there are some obvious observations. As you can see, if a resolver is to win the MBRG, then metric dimension should be at the most order of the graph divided by 2 lower. Whereas if a metric dimension is at least ceiling of the order of the graph divided by 2 plus 1, then you don't have enough steps to occupy the minimum resolving set. Therefore, outcome will be that spoiler wins. And there are some other inequalities. Next. So this, there are 2 important concepts. So we don't have if and only if result at all with respect to MBRG games, but there are 2 important concepts. One is called twin equivalence class. This one actually leads us toward getting some results such that the outcome, if certain conditions are met, outcome is that the spoiler always wins. Whereas there's another concept called a pairing resolving set that would lead to a concept that guarantees that resolver wins in the MBRG. So what is a twin equivalence class? So the open neighborhood of a vertex U is an open U is the collection of vertices X, such that X and U is an edge. Now 2 vertices are called twins. If you have the 2 vertices having the identically same neighbors excluding themselves. And notice that a vertex is its own twin, and Hernando et al. Observed that the twin relation is an equivalence relation, and that an equivalence class under it, hereafter we call it as a twin equivalence class, induces either a clique or an independent set. So this is an observation due to Hernando, Mora, Polaro, Sierra, Wood. So let W be a resolving set of a graph G. If X and Y are distinct members of the same twin equivalence class of graph G, then W intersection X, Y is non-empty set. So as you can see, if you have many vertices in the same twin equivalence class, then all but one should belong to any minimum resolving set. So this is going to play an important role. Next. So next. Thank you. So I'm going to combine this together. So if a graph has twin equivalence class of cardinality at least 4, which is the first graph on the bottom, then as you, by earlier result by Hernando et al., you have to have at least 3 vertices belonging to any minimum resolving set. And after second round, you know that the spoiler would have occupied 2 vertices. So the outcome would be that spoiler wins. And if you look at this, so that third one, the first graph is the demonstration of the first bullet. In this slide. And if you look at the second graph, is a demonstration of the second bullet. So now the second one, if you look at it, there are 2 distinct twin equivalence classes. Each of them has cardinality at least 3 situations, let's say 3. Then for the first 2 red circles, right? From this one, you have to occupy 2 vertices to form a resolving set. From here, you have to occupy 2 vertices to form a resolving set. And spoiler is guaranteed to pick 2 vertices after the second round, either from the first 3 vertices or the second 3 vertices. The reason is that if a spoiler plays first, it's guaranteed that he would just pick the first 2 vertices from either of them. Whereas if a resolver picks 1 vertex from one circled red one, then spoiler can go to the other part and pick the subsequently 2 vertices. So that's the reason. So the first and second, those are the general result of the bullet. This would be important in terms of the characterization of the outcome of MBRG for any tree, in fact. Next. So the next one is a result towards leading us to see that the MBRG's result outcome should be that resolver wins. So let's see what happens. So a set S, which is consisting of a set of 2 subsets, U1W1 as one element, U2W2 and UKWK. And then all of them are distinct. So that's where your union of that being 2K. And this is set A is called a pairing resolving set of a graph G if every set x1 through xk, where xi is either ui or wi for each I is a resolving set of graph G. So whether a resolver played first or second, regardless, whenever if a spoiler picks, say, u1, then resolver is guaranteed to pick w1 because you're alternately doing things, right? So that's the reason. And if A is a pairing resolving set of the graph with a cardinality being the same as metric dimension, we are going to call it a dim dash pairing resolving set of a graph G. So requiring the minimum number of steps possible. Next. Yeah, so next. So I'm going to skip some part of it if it is a little bit less necessary given time constraint. So this is an example of pairing resolving set on the outcome of MBRG. So if you look at this graph, so there are 3 blue boxes. So what it does is that the 2 vertices in each blue box would be forming an element of a pairing resolving set. If you just pick exactly 1 vertex from each blue box, 3, right, total, then you are going to form a resolving set. And in fact, it's going to form a minimum resolving set. So this is a situation where a pairing, the graph admits a pairing resolving set. Therefore, the outcome is that resolve always wins. So by the way, I need to mention this concept as to where did we get the idea of pairing resolving set. So to Chen et al. In 2020, when they studied the maker-breaker domination game, they introduced the concept of pairing dominating set. So it's an analogous concept. So we just used that in terms of a resolving set. So that's what it is. Next. So now the question is this. So until at the moment, we had a bunch of results in terms of trees and certain graphs, blah blah blah. And then what we found out is that if the outcome happens to be that resolver wins, the minimum steps required happen to be the same as metric dimension. If the spoiler wins, then usually the number of steps needed was 2. So we wondered, well, is there a graph G such that the number of steps, minimum number of steps required for resolver to win when resolver plays first is strictly bigger than metric dimension of the graph? And the answer is yes. So let me describe this graph a little bit. So I will go to the picture directly. So you have 1, 2, 3. So that is the vertices consisting of 1, 2, 3. That is called A, set A, vertex set A. And then if you move forward, there's 7 vertices in the dotted circle. That's vertex set B. And the one next to it, the 7 vertices again, that's vertex C. So A, B, C, they are all forming cliques. Further, so if you look at the set B in the middle, the dotted one, those are basically 2 to the number of vertices in A minus 1, because your subscript is going to be just the power set of the vertex set A, excluding the empty set. So what do we do? If you have B subscript set of 1, then that vertex should be adjacent to 1 in the set A only. The other way around, and this should go the other way.
Oh yeah, this one.
And then if you go down B subscript 1 and 2, let's go down vertex in the middle in the set B. Then B subscript 1 and 2, that is going to be adjacent to both the vertex 1 and 2 in the set A. And between the vertex subset B and C, what happens is that when they have the identically same subscript, they have edges, otherwise there are no edges. So that's all possible scenarios. Next. So this requires some work to prove, but what we were able to show is that in fact, the vertex set, in this case, the vertex set A is a set consisting of 1, 2, and 3. They in fact form a minimum resolving set. Not only that, they are this is a unique minimum resolving set of this graph. So as you can see, after the second round, whether even make or break resolver plays first, spoiler can always occupy 1 vertex. And because it's a unique minimum resolving set, basically there's an issue, right, for resolver to occupy all vertices, minimum resolving set within the metric dimension of a graph G unit of time. Now, on the other hand, we separately showed that if you have B sub S, comma C sub S as two subset element, where S is a subset power set of element of power set of A, which is not an empty set, they form a pairing resolving set of a graph G. So resolver is guaranteed to win, yet this is the situation that R sub MBRG, the minimum number of steps for resolver to win in the resolver plane first situation, metric dimension is strictly less than that number of steps required to win. Any questions? Next, are you guys following my talk, or am I losing you?
Fine.
So, so I will just move on. So terminologies on trees. So this would be needed for us to mention about the characterization of the outcome of MBRG for trees. So for a fixed tree T, a leaf or end vertex is a vertex of degree 1. A major vertex is a vertex of degree at least 3. So a leaf is called a terminal vertex of a major vertex if L is called a terminal vertex of major vertex V if the distance between L and V is less than, strictly less than distance between L and W for every other major vertex W. So let's go to the first subtree. When you look at the first guy with the V1 being major vertex, L11, L12, L13, these guys are basically terminal vertices of V1. Why? Because if these three leaves, the closest major vertex to these guys would be V1. So we are going to say V1 is a major vertex with a terminal degree 3, and L11, L12, L13, those guys are terminal vertices of V1. So that's going to be on the right-hand side. If you look at L sub 21, this is in fact a leaf, but that is the major vertex. V2 is the closest major vertex to L sub 21. So we are going to say that L sub 21 is a terminal vertex of V2. That's the only one, and terminal degree of V sub 2 is 1. Likewise, now if you look at V sub 3, no leaf would be closest to V sub 3 among all the major vertices. So in this case, terminal vertex of V sub 3 equals 0. So we are going to denote by EX of T indicating the number of exterior major vertices of graph tree T. What is an exterior major vertex? Exterior major vertex is a major vertex that has terminal degree at least 1. So V1, V2, V3, V4, V5, among all these major vertices, except V3, which has terminal degree 0, all others have terminal degree being positive. So in this tree situation, exterior major vertex of this tree is 4, and sigma T is the number of leaves of this tree, and you can count quickly. Number of end vertices, degree 1 vertices, we have 8 of them. So what is the metric dimension of this tree? The metric dimension of the tree is a sigma T minus EX of T, as long as T is not a path. Remember, if you have a path, metric dimension is just simply 1. So this is the situation. So the next talk would slide would indicate how to pick a minimum resolving set. So if you look at V sub 1 subtree, let's go back to V sub 1 again. You have you can view 3 paths: V sub 1, L11, V sub 1, L12, V sub 1, L13. Out of these 3 paths, excluding V sub 1, then you would have basically 3 disjoint paths. Out of those 3 disjoint paths, what we have to do is you just have to pick only exclude only one path. Out of these 2 paths, you have to pick 1 vertex from each path. Then they form a minimum, resolving set in this case. So with respect to V2 and L21 path, you have only 1 path, so terminal degree being 1. So in that case, you don't have to pick any vertex to belong to any minimum resolving set, etc. So can we, next please. So this is a result of a tree that is not a path. Next dimension is just sigma t minus x of t. Again, sigma being number of leaves of the tree, minus xt being number of exterior major vertices. That is number of major vertices with a terminal degree at least 1. So this was the result was obtained by 3 groups. Next. So this is the Poisson and Zhang's result that actually characterize all possible minimum resultant sets. So that was what I was describing to you. If you have let's say rooted tree at a major vertex and the rest of them are degree at most 2, except the one major vertex, out of the path, excluding that one, you pick all but one and pick exactly one vertex from each path, then they form a minimum resultant set. That's what the result is. And this actually, together with the concept of a twin equivalence class, that allows us to characterize the outcome of a tree. Next. So we are denoting some notations when capital M of T be the set of exterior major vertices of tree with terminal degree at least 2. The reason we restricted to terminal degree at least 2 is that if you have terminal degree 1, then no vertex needs to be in any minimum resultant set. That's why we restricted at least 2. And for each vertex, major vertex of terminal degree at least 2, let L sub V be the set of terminal vertices of V in T. So the outcome is in such a way that it depends on, so each major vertex, how many leaves are adjacent to these major vertices. So remember, if you have at least a twin equivalence class with 4 members in the same equivalence class, then result always wins. That's the first one of S. If you have 2 distinct twin equivalence classes, each of them having 3 members, so that then spoiler wins. Did I say reservoir earlier? So spoiler wind, both the cases are the spoiler wind. So those are the first and second one under the category of this one. For the outcome of tree, when you have exactly one major vertex with 3 leaves, exactly 3 leaves attached to that one major vertex, and the rest of them, you would have at most 2. That is the situation where the first player wins. And if any major vertex, you have at most 2 leaves adjacent to it. You can have many leaves, it doesn't matter. But if you have only 2 leaves exactly adjacent to major vertex at most, then result is guaranteed to win. Next. So this is a demonstration. So if you look at G1, G2, so the first top graph, you have 4 leaves adjacent to a major vertex. The second one, the vertically down, you have 2 equivalence classes with exactly 3 members in each twin equivalence classes. So those are the situations that spoiler wins. If you look at the middle graphs to G3 and G4, then you have there are 1 twin equivalence class of cardinality 3. And the rest of them are at most 2. In that case, the first player wins. Now, if you look at G5 and G6, for each major vertex, you can have at most 2 vertices adjacent to each major vertex. So G5, you have 2 twin equivalent classes of cardinality 2 each. Now, if you look at G6, you can have many leaves, but you have some additional length so that you can pick and choose from. So that allows us to resolve to win. Any questions? So that we were fortunately able to completely characterize tree situation on the outcome of MBRG. Next. So the next one is about bouquet of M cycles. So bouquet of M cycles, we denote by B sub M, is a bouquet of M cycles. So if you look at this graph B4, you have actually 4 cycles. So what is a bouquet of M cycles? You consider just arbitrary M cycles, length of whatever you want, at least 3. And then you pick one vertex exactly from each cycle and identify that one vertex. So that's why we call it a bouquet of M cycles. And there's only one vertex situation. Isawadi, Bascaro, Selman, Siman, Juntak proved that the metric dimension of a Bouquet cycle is number of cycles if the graph has all other cycles only, or if it has even cycle, then number of cycles plus number of even cycles minus 1. So if you have even cycles, you can just select 2 for each. You have to select in certain ways anyway, but minimum they establish the bound, and you have to select 2 from each even cycle, excluding 1 even cycle. So that's the situation. Next. So with respect to, it's kind of funny, with respect to bouquet of cycles, when you have the outcome depended on how many 4 cycles we had. If you have at the most 2 4 cycles, the outcome is that resolve always wins. If you have exactly 3 4 cycles, then the first player wins. Whereas if you have at least 4 cycles, the spoiler wins. So the rationale is this: if you look at the bouquet of 4 cycles and the further left one, that cycle is in fact 4 cycle, and the vertex adjacent to that cut vertex, 2 vertices adjacent to the cut vertex, they form a twin vertices. So that's the rationale actually. So if you have enough, then you pick only one of the twin vertices. What happens is that if you have lots of 4 cycles attached to it, right? So the ones that are not attached to it, they actually happen to have exactly the same codes. So you got to remedy that somehow. So that's the rationale. So bouquet of cycle gives us some interesting results. So next. So I think this is the last slide with respect to MBRG. So with respect to the metric dimension of the Peterson graph, the Cartesian product of 2 paths or Cartesian product of 2 cycles, they were obtained by other authors. And we kind of, for the Peterson graph, we had to explicitly determine all possible minimum resolving set. Peterson graph is a vertex transitive and edge transitive. So you just fix one vertex and you can kind of compute all of them like case by case. And then we were able to do so. We were able to show that the outcome for all these graphs, Peterson graph, Cartesian product of 2 paths, Cartesian product of 2 cycles, they are all that resolve always wins, whoever plays first. With respect to the Cartesian product of path, they actually admit a pairing resolving set. Pairing resolving set. So, and the Cartesian product of cycles, it just needs a little bit more work because you got to divide by at least one of CS Cartesian CT. You have to show that at least one of them being odd versus both of them even situation. It requires a little bit of work, but doable. Next. So now we are going to, so I still have about 15, no, I don't have 15 minutes. I still have 10 minutes. So the next one I'm going to talk about would be the fractionalization of it. So at first I put this part in the beginning and I realized it would confuse people. So I moved it out to the end. So I need to mention to you what a fractional metric dimension is. So if you remember, so that's the first thing I need to mention. And then how do we apply the rules and the general outcomes, etc. So the interesting part here is that when you fractionalize it, you could have an outcome of MBRG being resolve always wins, but you could have all possible scenarios that would occur when you fractionalize it. Resolve could win, or examples for which resolve wins, or first player wins, or spore wins. They all appear. So this is kind of interesting. So the fractionalization of various graph parameters have been extensively studied, and then this book is mentioned by many authors. So I mentioned this book. Next. And Curry and Ollerman defined the fractional metric dimension as the optimal solution to a linear programming problem by relaxing a condition of the integer programming problem for metric dimension. So what they did is that they actually formulated the integer programming problem, but then if you, instead of integer, you allow real numbers, then that's what it is. So just get rid of the integer condition. So, but they didn't get into the details. They only formulated that. Next. And the people who actually officially studied are Arumugam and Matthew on the fractional metric dimension. Next. Next. So for a function G defined on V, and for U being a subset of V, G of U is a summation of GS, where S is an element of U. So what we do is that if you remember for resolving set, each vertex is assigned either value 1 or 0. So it's assigned to 1 if that vertex belongs to a minimum resolving set, and 0 if it doesn't belong to a minimum resolving set. That's one way you can look at it. And you sum up all the values assigned for vertices and look at what the minimum cardinality would be that forms a minimum resolving set. With respect to resolving function, is that we are allowing any value greater or equal to 0, less or equal to 1. So the second bullet is that a real valued function G from vertex set V to this is closed interval real numbers from 0 to 1 is a resolving function of G if G of R of x comma y is greater or equal to 1. If you remember, R of x comma y is the vertices that distinguish x and y by distances. So the vertices that can distinguish x and y by its distances, those vertices values assigned under function G is at least 1 by summing up for any distinct x and y. So then we call it a resolving function. So the idea is that instead of assigning values 0 and 1, discrete values, you are assigning any real values. So as you can see that if, so that's going to be the next one. So what is the fractional metric dimension of the graph G, which we denote by dim subscript F of G. Subscript F indicating fractionalization of it is the minimum weight over the values assigned for each vertex under the function of a resolving function G. So you take all the possible minimum values, and then that is going to be the minimum fractional metric dimension of the graph G. Actually, compared to the metric dimension, there are sometimes irregularities appearing in terms of a metric dimension that gets smoothed out when you do fractionalize it. All those some irregularities, in fact, sometimes disappear. Next, so as one can expect, fractional metric dimension reduces to metric dimension if you look at from the second bullet for the codomain from the 0,1 interval real value interval. If you replace it by 0,1, right, discrete values, then that becomes a basically resolving set. Next. So fractional metric dimension of the graph is less or equal to the metric dimension of the graph. Next. So the same house graph as before. Now, if you look at the vertices R of A comma B, that means the vertices that resolves A and B would be A, B, and C, because D would be at equidistance from A and B, as well as E is at the equidistance from A and B. And R of A comma D is the vertices distinguishing A and D would be A, D, E. Now, if you look at two vertices B and D, the vertices that resolve B and D would be all vertices excluding A. A is the only one at equidistance. So what we are doing is that we are going to sum up the values assigned A, B, C under the function G, and that should be at least 1. And the values assigned for A, D, and E under the function G should be at least 1, as well as the values assigned for B, C, D, E under the function G should be at least 1. So there are 3 inequalities here. Now, if you look at these 3 inequalities, the interesting thing is that each vertex appears exactly twice. So when you sum up, you have twice of G of the entire vertex set is at least 3. So therefore, we are establishing the lower bound. The any minimum resolving function G of vertex set is at least 3/2. Next. So if you assign values inside of the vertices are big this time, right? So because I assigned the value for A being 1/2, B, C, the rest of them being 1/4, and they form in fact a resolving function. So therefore, in this case, fractional metric dimension of this graph is 3/2. So a lot of the irregularities get smoothed out, disappears in terms of fractionalization of the metric dimension. Next. So with respect to the rules are basically the same. So in the outcome, so this time, what is the difference? Instead of forming a resolving set, we wanted to see you assign values in such a way, can you assign values in such a way to form a resolving function instead of resolving set. That's the only difference. So with respect to outcome, I put subscript f to show that it's a fractionalization of it. Next. So if you have two distinct vertices that are forming twin vertices belonging to the same equivalence class, then one of them must belong to any minimum resolving set. Now, with respect to resolving function, we have, if a G is a resolving function of the graph G, and U and W are distinct twin vertices belonging to the same equivalence class, then GU plus GW is at least one. Next. So these are part that is comparable to what happens with respect to TEC stands for twin equivalence class. What happens with respect to the twin equivalence class with the cardinality certain things, and I need the additional restriction of fractional metric dimension being certain things, certain values, then I can establish these things. But if I try to go through it, it's too complicated. So I will demonstrate in the next picture. Next. So if you look at this corollary A and B, so this is a special case of the previous three results. Corollary A and B, if the graph has twin equivalence class of cardinality at least 4, or if you have at least 2 distinct twin equivalence classes of cardinality 3, then we saw that the outcome of MBRG with its spoiler winds. The same is true in this case. It's easy to show. However, the C is the difference. If you look at the third graph G3, you have 3 distinct twin equivalence classes of exactly cardinality exactly 2, and in this case, metric dimension is 3, whereas a fractional metric dimension is also 3. Actually, in that case, if a graph G, in this case, the outcome of the fractional maker-breaker game is that spoiler always wins. So the way we go about doing it is that out of this 1, 2, 3, right? So 3 twin equivalence classes with a cardinality 2 each. So resolver, let's just say resolver assigned value first, right? Assigned value A, B, C in such a way, C is the smallest one. A is greater or equal to B, B is greater or equal to C, and sum up of A plus B plus C equals 1. Then what spoiler can do is that assign values 1/2 into the vertex, the resolver occupied with the vertices assigned B, as well as for C, each of them assigned 1/2. Then whatever resolver assigned the next step in the second round, there would be a vertex set 2 vertices, twin equivalence classes with a value assigned at most 1/2. That's where the spoilers can just go in and then assign values. So that's why spoiler can always win. So that's the situation. So this is the G3, for corollary C, the situation, the actual discrepancy between a maker-breaker game versus fractionalization, the outcome becomes different. Next. So this is another situation where you have 1 twin equivalence class of cardinality 3. This is specific graph, but 1 equivalence class with the cardinality 3 and another equivalence class of cardinality 2. If you look at maker-breaker game, resolving game, the outcome is that the first player wins, whereas in this case, spoiler wins. So that's another discrepancy that occurs. Next. So this is a description of, we don't have the pairing resolving set situation. So this is a description as to when something gets pushed for resolver to win. And this is a kind of proof goes like more like algorithmically way. Something when you do certain ways, recursively, something is guaranteed. So that's a kind of result. Next. So this is a relevant result, which is that, so maybe I can just, so if you have a fractional metric dimension of tree is the number of leaves minus number of extreme major vertices of terminal degree exactly 1 divided by 2. So that's the relevant one. But next. So if I could take a couple more minutes, I think I can finish up. So this is a demonstration of the outcome of fractional maker-breaker game where resolver is guaranteed to win. So the first major vertex on the left in G has a terminal degree 3. So W1, W2, W3, what you could do is you can just assign values in W1 1/2, W2 1/2, W3 1/2 to make it easy, as well as the second extreme major vertex. you have terminal degree 2, so W4 and W5, both of them, we just assign values 1/2 each over all the vertices, sum up together. Now, then this G forms a resolving function of the graph with a value being 5/2. And further, the second part is important. Cardinality of Wi for each I is at least twice of the G of Wi, which is 1/2, so 2 times 1/2 plus 1, so at least 2. So this would guarantee, that's the demonstration of the complicated looking result earlier, indicating that if you have basically enough vertices in certain ways that would form some minimum resolving function for each, blocks, and if you have enough vertices for each block, then it guarantees that the fractional make or break resolving game outcome is going to be that resolver always wins. So that's the demonstration. Next. So I will just mention briefly. So if you have a maker breaker game, the outcome is resolver wins. You have in fact 3 separate outcomes. That next. When in a maker breaker game, if you have the first player wins, then when you fractionalize it, you have 2 outcomes. Either first player wins or spoiler wins. I was not able to find any situation where resolver wins in this case. Next. So that's the question. I don't know the answer to that. Next. Now, if you have the outcome being that in the maker breaker game, spoiler wins, then we have a situation where fractionalization result would be the same. Next. But I don't know if the outcome of maker breaker game is that spoiler wins, but fractionalization of it would be either resolver wins or first player wins. I don't have any result on this one at all, and I don't know if it is true or not. Next. So these are some references. So I put, I don't know if I think I put enough references. I believe that the 1, 2, 3, 4, 5. The 5th one is actually what motivated us to work on this one. And if you go to the next page, this talk is based on the second reference from the top and the second reference from the bottom. So just kind of putting some core content of those things. Next. Thank you. Any questions?
Thank you. Also trying to unmute. Thank you. Yeah, let's take the speaker. Thank you, Ji. Any questions for